Okay, we are now starting section 19.4, and this is about Voltaic cells. So we are gonna start exploring how taking redox reactions will allow us to harness that power, that electricity that it represents the flow of electrons between the reduction reaction and the oxidation reaction. Okay, there are two main types of electrochemical cells in this case. Okay, we have the Voltaic cells, which is the ones that we're gonna study in this section, and we have electrolytic cells. Um, from the point of view of redox reactions, they both use um, redox reactions. There will be an oxidation reaction and a reduction reaction happening simultaneously. The difference between the two is that the Voltaic cell generates electricity and the electrolytic cell uses electricity. So pretty much in a voltaic cell, you use the redox reaction to produce electricity, and in an electrolytic cell, you use electricity to make a chemical reaction happen that otherwise would not happen. Okay, the key to these two cells is that both the reduction and the oxidation reactions happen in separate containers. Okay, so if we take a look at one redox reaction here between copper and zinc, right? Remember, the reduction implies gain of electrons, the oxidation implies loss of electrons. So this number of electrons here has to be equal, and that represents the transfer of electrons between the two half reactions. So if you connect these reactions properly, and by properly I mean you guarantee the flow of electrons, they will still happen in separate containers. You don't need to have both reactants in close contact for this reaction to happen. Okay, so that's what we have to guarantee, that these the flow of electrons, that you maintain a flow of electrons so that the reduction and the oxidation reaction can happen. So, and we use a Daniell cell for that purpose, right? So we have the same reaction. We have copper and zinc, right? So we have zinc here, okay? And zinc, if you remember in this reaction, zinc is being oxidized, right? So in this side, we have zinc going to zinc 2 plus 2 electrons, okay? Those 2 electrons are being deposited here in this electrode, and in the other reaction, the other half reaction, we have copper going from copper 2 plus, gaining 2 electrons to go to copper 0. Okay, so in order to this reaction to happen, you have to provide the electrons. So pretty much in the left side of this cell, you collect the electrons, and in the right side of this cell, you deliver the electrons. Okay, because you require electrons in this case to the reduction reaction. Okay, this is the reduction, and you collect here because the oxidation reaction is providing the electrons. Okay, since this side, since you are collecting on this side, on the left side, this is sort of the negative side because it's reaching electrons, and the only reason those electrons are moving through the wire to the right side is because there is something that is consuming the electrons here. So this side is positive, it's consuming the electrons, so it's electron deficient in a way. Okay, now each one of these this particular collecting surface, which in this case is made out of zinc, so in a way, if zinc is being consumed, that bar there is being dissolved in the solution. Okay, so but that bar, whether it's made of the same metal that is participating in the reaction or made of another material, that is what we call the anode. Okay, and let's remember that the anode is the one collecting the electrons, so the anode is negative, and the bar that is collecting here the bar that is providing the electrons to the reduction reaction, that is the cathode. And the cathode, because electrons are being consumed there, is electron deficient, so the cathode is positive. Okay, now here is something that I want you to remember correctly. Okay, so where does each reaction happen? So the oxidation happens in the anode and the reduction happens in the cathode. So I want you to remember that those are vowels and these are consonants, so that you can relate properly what reaction happens in what electrode. Okay, and usually the anode is in the left side and the cathode in the right side. So let's put that as well, left and right. Now the other thing that is important here is that this reaction is not going to happen if you don't provide a salt bridge. And what is the purpose of the salt bridge? Well, you are producing ions or you are consuming ions. So notice that in this case, the zinc is being dissolved and you are increasing the number of cations in solution. But the solution has to be electrically neutral anyway. So if the charges of the cations have to be balanced by the charges of the anions. So the salt bridge here is providing the counter ion. So in this case, if you are producing cations, then it's providing anions so that you balance that positive charge being added to the solution. Okay? In contrast, in the other side, you are consuming cations. So the number of positive charges is decreasing in the solution. Therefore, you have to replenish those positive charges by providing more cations. Okay, so cations is being provided by, the salt bridge is providing both the anions and the cations, but the cations will go to the cathode side and the anions will go to the anode side. So just pay attention to what is happening with the ions, which one is being produced or which one is being consumed, and then you balance the ions accordingly. You have to provide the oppositely charged ion to that particular solution. You increase positive ions, then you have to provide negative ions. You are consuming positive ions, then you have to replenish the positive ions. Okay, as I said before, those metal bars in which you are either collecting the electrons or delivering the electrons, you call them electrodes. Okay, it's the surface in which the electron transfer actually happens. Okay, so the source of electrons is the negative one, that is the anode, is usually in the left side. That is where the oxidation happens. The anode is negative because it's collecting the electrons that are being lost in the oxidation reaction. Now those electrons move through the wire to the other side, to the other electrode, which is positive. That electrode is positive because electrons are being consumed in that electrode. So you are removing electrons from that electrode, and then it becomes electron deficient. So the flow of electrons actually happens by that deficiency of electrons on the cathode. Okay, so that is the driving force in the flow of electrons, because you are consuming those electrons. It's not so much that the electrons being collected are being pushed through the wire. It's more a response to that deficiency of electrons that you have in the other side. And then you have to balance the ions, and for that purpose you use the salt bridge. If you produce positive ions, you need to provide negative ions. If you are consuming positive ions, then you have to replenish the positive ions. Now you need both the salt bridge and the wire to close the circuit, so to speak. Okay, if one of those are missing, then nothing is going to happen, because there is, number one, not a flow of electrons if there is no wire, or not a flow of ions if you don't have the salt bridge. In either case, there is no the flow of electric charge is going to be interrupted, and therefore nothing is going to happen. Okay, the wire allows the flow of electrons, positive charged particles in a way, and the cell bridge allows the flow of ions, charged particles anyway. Okay. Now that driving force that I was mentioning, that flow of electrons, well, that receive a number, and that is that receive a name, and that is the electrical potential. Okay, which we are going to be working later on. So right now we are just worried about properly writing and describing a voltaic cell, and then the next step is to how to determine the electrical potential for that particular cell. That electrical potential is measured in volts. So basically we are working with batteries here, right? What's common in all these voltaic cells? Well, number one, you are using redox reactions, so the reduction and the oxidation reactions happen simultaneously. Okay. Now the reactants are not in close contact, so that's why you have the cell bridge and the wire. The half reactions are happening in different containers, but because you can guarantee the flow of ions and the flow of electrons, then those reactions are still happening. Okay. So, and that reaction is going to happen as if those reactants were in close contact. So that if you were conducting the reaction in the same container, the same reaction will still be happening if you have it separated. Okay. So these reactions are spontaneous. I mean, if you can obtain electricity out of that reaction, then that is a spontaneous reaction. If nothing is happening, then the reaction is not favorable. It's nothing that you can actually use to produce electricity, and then that most likely would be an electrolytic cell, that you have to provide electricity for that reaction to happen. Okay, so that chemical energy, so you are harnessing the power of a chemical reaction to generate electricity, something that you can utilize. Okay, I mean, if you mix the reactants in the same container, well, the reaction happens, but you are not obtaining a benefit out of the reaction. I mean, a benefit other than the products that you are obtaining. But with a voltaic cell, you get, if you are interested in the products of the reaction, then you can still obtain both the products of the reaction and electricity out of that reaction. So it's double the benefit, if you will. Now, how can we describe this cell without having to write the whole thing? Okay, so we use what we call the standard cell notation. Okay, so it's an abbreviation of what is happening in the entire cell. So you don't have to worry about drawing the cell bridge and what is contained in the cell bridge, or the whole picture of the anode, the cathode, and the containers, right? So you are just more interested in what the reaction really is. So in this particular case, this standard notation is describing the whole thing, and we are writing this pretty much in the same order that we see that picture. So you start with the anode, then the cell bridge in the middle, and the cathode goes to the far right. So if you picture this as the cell that we previously worked with, then you have, if this is the anode, right? And the anode, remember, the oxidation is happening in the anode, so it's the negative electrode, and this is the cathode, is the one where the electrons are going to go. So basically what you have to picture is that the flow of electrons is in this direction. Okay, so the electrons are going in that direction pretty much. All right. Now, features of this standard notation. You will notice single bars, vertical bars for that matter, and the purpose of those bars is to separate different phases. So for example, here you have a solid, but here you have a solution. Okay, so that bar is separating the fact that those two are in different phases. You have a solid phase and then you have a solution. Same thing here, so you have a solution here, but you have a solid there. And last but not least, you have a double vertical bar You will always see that, and that represents the cell bridge. Okay, it's not only separating phases, although in this case they are the same phase, but it represents the cell bridge. It's the one that is going to provide the flow of ions. So in this case, let's use first, let's picture what is happening here, right? So silver ions are reduced to silver metal. So how do we describe that? So we have Ag plus. If it's being reduced to silver metal, then it's gaining electrons. So this is a reduction. And copper metal is oxidized. Copper 0 is oxidized to copper 2 plus, and in this case has to be 2 electrons. This is the oxidation. Okay, and well, where do they go? So the reduction goes to the anode. Sorry. The reduction goes to the cathode, and the oxidation goes to the anode. Okay, so this reaction is actually happening on this side. Ag plus 1 electron goes to Ag 0. Okay, and this is a solid because it's a metal, and this is in solution. And in the left side, what you have is the copper metal going to copper 2 plus in solution plus 2 electrons. Okay, so how do we describe this? So you are going from copper, so the bar here is copper, and you are providing copper 2 plus to the solution. That doesn't look good. Copper 2 plus to the solution, so electrons are being collected here. Alright, you have silver metal here, so this bar is made out of silver, and silver ions are being removed at the bar, so the electrons are coming this way. Alright, and since you are generating ions here, then you must provide, let's say you are using a salt bridge with potassium nitrate, so nitrate is coming this way, and you are consuming positive ions here, so you have to replenish those, so potassium plus is going there. Okay, so that's how you describe your full Daniell cell. But we want also to write our standard cell notation, right? So how do we write our standard cell notation? Well, we start with the anode, correct? So the anode is here. And usually you start with the electrode. And what is the electrode made out of? So the electrode is copper, solid. And copper is separated from the solution containing copper 2 plus. Okay? And then you have the cell bridge. And then the cell bridge is connecting with a solution containing silver ions. And silver is separated from the electrode, which is made out of silver as well. So this is our standard cell notation for this Voltaic cell. Okay, you have the anode, you have the cell bridge, and then you have the cathode. Okay, successfully writing the standard cell notation means you have to correctly identify which one is the reduction reaction and which one is the oxidation reaction. And remembering that the oxidation happens in the anode, once again, the vowels, and the reduction happens in the cathode. Okay, here the consonants. All right. Now in this particular case, we have iron 3 ions being converted to iron 2 ions. So that is iron 3 plus is going to iron 2 plus. So the oxidation number is getting less positive or more negative, so that is actually a reduction. So iron 3 is gaining an electron. And then tin is oxidized to tin 2 plus. So we have 2 electrons here. Okay, so this is the oxidation, this is the reduction. Okay, therefore this is the anodic reaction, this is the cathodic reaction. So we don't really need to go and draw the full cell, we can just go with the cell notation, right? So we start with the anode, right? So this is a solid and this is in solution, but here we have a problem because the iron is both in solution. Okay, so let's just start with the anode. So we have a bar of tin. Okay, whenever you have the metal in the solid form, you can assume that that metal is the electrode. Okay, so in this case for the anode, the tin is the electrode in that side is the a bar of tin, and that is separated from a solution that contains tin 2 plus. Okay, just to mention, there is here mentioning standard conditions, and what that means is that for standard conditions, okay, let's write that down here. Standard conditions means that if you have a solution, it has a 1 molar solution, and if it's a gas, is 1 atmosphere gas. Okay, so for now let's just omit that. So we have a tin electrode in contact with a solution containing tin 2 plus. We have our salt bridge. Now what we have in solution, both of these are in solution. So technically what you have in that solution is iron 3 plus and iron 2 plus. So you separate them with a comma. Okay, but then what is the electrode? Because there is no iron, so technically, because iron is part of the reaction, you shouldn't use an iron bar, because then you are not having the reaction that you're expecting. So in that case, you use an inert electrode, and that inert electrode could be platinum or sometimes could be carbon. Okay, it depends on the application. Okay, so in this case, you just add this inert electrode to complete your circuit, because you need a surface in where to transfer the electrons. Okay, so you need an electrode, no matter what. So even if a solid metal is not involved in the reaction, you still need a surface in which to transfer the electrons. Okay, remember, the electrons are coming from a wire, so somehow you need to transfer those electrons into the solution, to whatever it is that is reacting. So that electrode is the one providing the surface, and if you don't have something that participates in the reaction that is a solid, then you need to use an inert electrode. So this is our final standard cell notation for this particular reaction. Okay, so whenever it comes to spontaneous reactions, redox reactions, you can always, if you connect them properly, you can harness the electricity out of that reaction. That involves that you are separating the reactants, so that you can harvest those electrons. I mean, if you don't separate them, then the transfer will occur directly between the reactants, and then you will not be able to collect those electrons. And in order to establish that flow of electrons, you need the wire, but you also need to guarantee the flow of ions. In what direction the ions flow? Well, it depends on what the particular reaction is, but you will be either generating ions or consuming ions. In each case, you will have to provide you will have to counterbalance the ions being produced or consumed. Okay. We call Voltaic cells to those that produce electricity. If it doesn't produce electricity, normally that would be an electrolytic cell. We will discuss that at the end of the semester. Okay. Important things to remember: the oxidation occurs in the anode, the reduction occurs in the cathode. So very important things to remember here. And the standard cell notation is what allows us to describe, instead of drawing the whole picture of a Daniell cell, you just use a one-line description that provides exactly the same information. When it comes to a cell bridge, it doesn't really matter what ions you are providing in that cell bridge, as long as they are not participating in the reaction. That's one important thing. But you can use anything. You can use potassium nitrate, sodium chloride. It depends, as long as it doesn't participate, they don't participate in the reaction. Okay.